Hello, in this video we're going to look at some additional minimum and maximum problems, and I encourage you to treat this like a problem solving session. Go ahead and try each one of these questions before I do them. Pause the video now and try this first one, see what you come up with, and then watch the video and see where my solution is the same as yours or where we differ. It's always better to try problems, at least see if you can get started, rather than just watching problem after problem. So I'm assuming you gave it a try, and let's try the first one here. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Well, that makes sense. We want to have the biggest field possible for the fencing we have. So let's draw our diagram here. We've got a little river. Maybe I'll draw that in blue. So here's our river. And then we're going to do some fencing, make a rectangular fence. So maybe call this X, call this Y. And we want our area, which is equal to X times Y. We want this to be maximized. Well, we can go ahead and find another equation, which is, of course, the perimeter. So the perimeter would equal to x plus y, and we know the perimeter is 2,400. So 2,400 equals x plus 2y. Looks like I could isolate for x, so x is 2,400 minus 2y. So that gives me area is equal to 2,400 minus 2y times y. Now, we can expand that, of course, to make our calculus a little bit easier. So area is equal to 2,400y minus 2y squared. Now, if you actually think back to grade 11, you could solve this problem without calculus. What you would do here, because you have a parabola, is we're trying to find the highest point on that parabola. Clearly, it's opening down. So it's going to have a vertex that's at the top, and then it's going to open down from there. And to find the vertex, you need to, of course, complete the square. And so if you wanted to, for fun, you could try to do this problem without calculus. You could use your grade 11 skills. You could complete the square, find the coordinates of that vertex, and you would be able to find the maximum for this problem. You might have actually done this exact problem in grade 11. These were the types of problems you looked at. But instead, let's use calculus. So a prime will be equal to 2,400 minus 4y. We could factor out a 4, and we'll get 600 minus y. Quick sign diagram over to the left. 600, negative, positive, increasing, decreasing. We should probably add that domain. Y must be positive. So all this gets crossed out because it's not in the domain. Very clearly, we get y equal to 600 is our max. And to find the dimensions of the field, we just need to plug that in for x. So we take this, plug it in up here, and we get x is equal to 2,400 minus 2 times 600. So 2,400 minus 1,200, so 1,200. And so our final answer is that the dimensions of the field are 1,200 feet by 600 feet. And again, for me, the fact that we can do this with calculus is a really interesting and fun, and personally, I never really liked completing the square. It felt very tedious, but taking the derivative here, that's actually quite enjoyable, at least for me, and hopefully you find it fun as well. You just bring the 2 down, a little bit of factoring here. Those types of skills, I think, are a little bit more common than completing the square, and it's cool to see how this old problem that was done with completing the square can now be done quite easily using calculus. So here's another rectangle problem. Find the dimensions of a rectangle with perimeter 100, whose area is as large as possible. So similar to the other one, but this time we don't have a river. So we just have our x and our y. Area is equal to xy. Perimeter is equal to, well, 2x plus 2y. So 100 is equal to 2x plus 2y. I want to isolate for, let's say, x. So 2x equals 100 minus 2y. So x equals 50 minus y if I divide everything by 2. So here what I did was I divided by 2. Okay, so that gives me area is equal to 50 minus y times y, or area is equal to 50y minus y squared. A prime is equal to 50 minus 2y, or 25. I should factor that 2, so 25 minus y. Draw a little sign diagram over at 25, negative, positive. Y has to be greater than 0, so I'll get rid of all this, which is not in the domain. And so clearly I have my maximum at y equals to 25. And I solve for x. X is equal to 50 minus 25, which is 25. Now, something to note here that's interesting is that the dimensions are equal. X and y are the same, which makes sense because of all the possible rectangles that you could make with 100 meters of fencing, the largest rectangle possible is actually the square. The square is, in some ways, like the best rectangle if you were thinking about it in terms of making something out of it. So we'll write that down. The dimensions that maximize area are, make sure you include the units, 25 meters by 25 meters. Now, this doesn't mean you can just assume all questions are going to be squares and you can just find the answer willy-nilly. We do still need to do calculus on these questions to actually find these values, but sometimes the value will make sense. It's just that you probably couldn't have guessed it initially. It only makes sense in the end once you've actually seen it. Let's find the point on the line y equals to 2x plus 3 that is closest to the origin. All right, so we should graph that line. 1, 2, 3, so we've got a y-intercept there. The x-intercept would be at 2x plus 3 equals to 0, so 2x equals negative 3, x equals to negative 3 over 2. Okay, so we can get an x-intercept there. There's our line. And we're, of course, wanting it to be something like that. We want to find that point that's closest to the origin at 0, 0. This would be the point x and y. And we want d to be as small as possible. Well, what is d in this case? We need to use that distance formula. So x2 minus x1, y2 minus y1. So we get x squared plus y squared. Now we need to, of course, minimize, and we need to get rid of that y. So we're going to get x squared plus 2x plus 3 squared. Because this point xy isn't just a random point, it's x comma y, where y is equal to 2x plus 3. It's always on that line, so we can sub it in there. So if we keep working on this, we have x squared plus 4x squared plus, if we expand that out, we're going to get 12x plus 9. And so we keep working. 5x squared plus 12x plus 9. Good idea to do d squared. So let's do, let fx equal d squared. So fx will just be the same, but no square root, which is just so much nicer for doing calculus with. Square roots are ugly, so we get f prime is equal to 10x plus 12. Factor out the 2, 5x plus 6. Draw the sign diagram. Got our point at negative 6 over 5. Positive, negative. Now, there is no domain restriction here because x could be any number, but we see the value It's very clear the minimum distance happens at negative 6 over 5. So for y is equal to 2 times negative 6 over 5 plus 3, because we know y is equal to 2x plus 3. So we'll get negative 12 over 5 plus, well, 3, we should probably do common denominator here. So over 5 times 5. That will give us negative 12 plus 15 over 5. So 3 over 5. And so we've got our final answer. The point closest to the origin is negative 6 over 5 and 3 over 5. And there we have our answer. Let's find the dimensions of a rectangle of largest area that can be inscribed in a circle of radius r. Alright, so we have our circle. And we're going to draw a rectangle inside here. So something like that. Now, the rectangle would have dimensions, let's say, x and y. So our area is going to be xy, and this is what we want to maximize. We haven't included the fact that there is a radius here. So let's be sneaky, and let's draw the radius like this. Oh, draw that a little better. Right to the corner. Well, if we do that, then we could draw another radius to the other corner. Because we need some other equation, and this equation is what we're going to need. X squared plus y squared will equal 2r squared, because the hypotenuse there is going to be 2r. Alright, so we get x squared plus y squared equals 4r squared. I'm going to go ahead and isolate for x. So x squared equals 4r squared minus y squared. So let's get rid of that square with a square root. 4r squared minus y squared. So we're going to go ahead and sub that in, and that would give us a is equal to square root of 4r squared minus y squared times y. So again, I don't really want to do that square root. You could, but it's messy. So I'm going to let f of y, I guess in this case, f of y equal to a squared. And so I'd have f of y as 4r squared minus y squared times, well, when I square the other part, of course, I have to square the y. So 4r squared y squared minus y to the 4. Right, if I square a here, a squared, I have to square the whole thing. And then I'd also have the y here. This all needs to square, so the square will go to the root, and the square will go to the y. Alright, so that's just an aside here. So we've got our f of y equation, and we'll do the derivative. Again, the 4 is a constant, the r is a constant, so this will become 4r squared times 2y minus 4y cubed. Okay, well, we got definitely some factoring to do here. This is a little bit tricky. There looks like a 4 in common and a y, so we'll factor that out. That'll leave me with 2r squared minus y squared. I think I can do a difference of squares here. So root 2r minus y, root 2r plus y. So that would give y equals 0 for the first root, y equals root 2r, and y equals negative root 2r. So let's put those in a sign diagram. So we've got 0, we've got root 2r, and we've got negative root 2r. So this will give us, well, notice that negative on the y, so we're going to have a negative sign over here, because when you put in a big value, this will be positive, but this will be negative, so negative times positive is negative. Negative, positive, negative, positive. We should note that y must be positive. That's our domain. Which means right here, we can cross all this off because it's not in the domain. So it's not relevant for our picture. All we need is the increasing, decreasing. Oh, there you have it. There's the maximum happening right at root 2r. So we're going to go ahead and use that to solve for x. So if y is equal to root 2r, then x is equal to the square root of 4r squared minus y squared, which would be equal to the square root of 4r squared minus, well, let's just see here, y squared would be root 2 will give me a 2r squared, so 2r squared, square root of 2r squared, which is, oh, look, root 2r. The dimensions are root 2r by root 2r. And again, this is what we found earlier, but this really shows that of all the rectangles, the square, the one where the two dimensions are the same, the square is the best rectangle, which I think is very interesting that that's indeed the case. It's not always the case when there's rivers involved or other cost functions, but if we're just talking about a pure rectangle being inscribed in a circle, you bet that the best one you could do would be a square. The top and bottom margins of a poster are each 6 centimeters and the side margins are each 4 centimeters. If the area of printed material on the poster is fixed at 384 centimeters squared, find the dimensions of the poster with the smallest area. So this type of poster question is definitely common, and you need to know how to do this setup because it's tricky. So what you have is you have a poster, and then inside you have a smaller printed area with margins. Now, you can set this up either way, but I'm going to call this printed area X and Y. Now, the overall poster is obviously not XY because there's some margins. So there's 6 centimeters on the top and bottom. So this distance here is 6. This is also 6. And this is 4. And this is 4. So if you're looking at the overall width of the poster down here, this overall width is going to be not X, but it's going to be X plus 8. And the overall length of the poster, or height of the poster, is going to be not Y, but Y plus 12. And so the area that we're going to be maximizing, or minimizing, I guess in this case, is the poster. This is what we want to minimize. So we need to make sure that those margins are included. Now, obviously there's 2 variables, and so we have to do something else here. And we know that the printed area, so this portion here, that's got the printing on it, this portion is going to be equal to 384 centimeters squared. Hopefully your poster doesn't look like that. Maybe have some more interesting printing rather than just some random red lines. But this 384 is equal to X times Y. And so we can isolate for Y as 384 over X and plug that in right here. So we'll get area is equal to X plus Y times 384 over X. Now, 384 over X plus 12, sorry, plus 12. Now again, we want to multiply this out before we do calculus. So let's do a little FOIL. So first will give me just 384. I guess we could put the times X over X, but those will cancel. And then outside, 12X, inside, 8 times 384 over X, and then last will be 8 times 12. So if we clean this up a bit, we get A equals 384 plus 12X plus, and I'm going to leave this as 8 times 384. I'm not going to actually do the multiplication yet because I may need to factor later. And I'm actually not going to do the multiplication here because you might know 8 times 12, but you actually don't need to. Because when we do the derivative, 8 times 12 is a constant, and it's just going to disappear. So I'm not going to bother multiplying this out or combining it with the 384, because I'm doing calculus now, and those are gone. So I just get 12 minus 8 times 384 over x squared. So we're going to go ahead and simplify this. So we're going to put this over x squared. So that'll give me 12x squared minus 8 times 384 over x squared. I'm going to factor a 12 out. And, well, how can I factor a 12 out of 384 and 8? You could factor, let's say, the 384, does 12 go into 384? Or maybe the 12 goes into the 8. You have to do a little bit of math here, but whatever you figure out, you should get 12 times 32 is 384. So you can factor the 12 out of the 384. And so I can go ahead now and keep working on my a prime. So I've got to factor this. I'm hoping it's a difference of squares. Well, 8 times 32. We could rewrite that as well to be equal to 12x squared. You can steal a 2 from the 32 to make it 16, and that'll make the 8 also a 16. So a little bit of fancy math there to help. The difference of squares is just x minus 16, x plus 16. So quick sign diagram over to the side. We're going to get 16, negative 16, and 0. Of course, we're going to have to cancel everything on that left side anyways, but we'll draw the full sign diagram to start. So positive, negative, negative, positive, increasing, decreasing, decreasing, increasing. But we know that x has to be positive. So this right here is not in the domain. So that gives us x equal to 16, which we can solve y equal to 384 over 16, which if you do the division, you'll simplify it as 24. So the dimensions of the poster are, and here is where you need to be very careful, because they're asking for the dimensions of the poster. If I write the dimensions of the poster are 16 and 24, is that correct? Well, let's look back at the original setup. X and Y are the dimensions of the printed area. The dimensions of the poster are x plus 8 and y plus 12. So I can't leave the dimensions of the poster as 16 and 24. Oh no, I have to go x plus 8. So 16 plus 8, which is going to give me 24, and y plus 12, which is 24 plus 12, or 36. So the dimensions of the poster are 24 centimeters by 36 centimeters. So notice that. Just because you solve for x and y doesn't always mean you solved for the values you were looking for, especially in a setup like this where there's a size of a printed area and a size of the poster. You need to be careful for what they ask for and that your variables match up with what they're asking for. So in this last example here, we have a piece of wire 10 meters long cut into two pieces. One piece is bent into a square and one piece is bent into a circle. How should the wire be cut so that the total area enclosed is maximum? Well, we have our wire, that's 10 meters, and it gets converted into a square and a circle. Square, I guess, would have sides x and x, circle with radius r, and we want the area, which I guess would be x squared plus pi r squared. We want this to be maximized. So we clearly need to get rid of one of those variables, and the perimeter will help us out. So we know that the perimeter of these two shapes would be 4x plus 2 pi r using circumference. And so 10 equals 4x plus 2 pi r. We can divide by 2 to give us 5 equals 2x plus pi r. And then we have to decide which one we want to substitute in for. I'm going to go ahead and solve for x. So 2x will equal 5 minus pi r. I just don't want to divide by pi. I'd rather divide by 2. So 5 minus pi r over 2. So that will give us area is equal to 5 minus pi r over 2 squared plus pi r squared. So let's go ahead and expand that out. We'll get to 25 minus 10 pi r plus pi squared r squared over 4 plus pi r squared. And to do the calculus, it'll just be nice to have each one of these as its own fraction, so we can avoid the quotient rule. So 25 over 4 minus 10 pi r over 4 plus pi squared r squared over 4 plus pi r squared. All right, let's do some calculus. So we're going to get area is equal to, well, the first one's a constant, so that's gone, minus 10 pi over 4 plus 2 pi squared r over 4. Then we're going to get plus 2 pi r. Again, our goal is going to be to get common denominator, but we can simplify first. This will become minus 5 pi over 2 plus pi squared r over 2 plus, well, I guess if I put this over 1, I could multiply by 2 and multiply by 2 to give me 4 pi r over 2. So it'll be minus 5 pi plus pi squared r plus 4 pi r over 2. So I need to, I guess, set this equal to 0 in the top. So I would set negative 5 pi plus pi squared r plus 4 pi r equal to 0. Again, it's a bit tricky with the algebra here, but we should be able to solve it if we move everything without an r to the one side and everything with an r to the other side. So that'll give us pi squared r plus 4 pi r equals 5 pi. Can factor out the r to give me pi squared plus 4 pi equals 5 pi. So r equals 5 pi over pi squared plus 4 pi. All right. Now we could actually reduce that a little bit. There's a pi in common, so we could get 5 over pi plus 4. Now we do need to look back at the original setup, because when we do our sign diagram here, we need to figure out what happens when we pick a number bigger than 5 over pi plus 4. And so if we look here, the r is going to be positive, and then this is a negative, but both of the r's are positive, so if we pick a bigger number, we'll get positive, and then negative. So decreasing, increasing. Which means, of course, we found our relative minimum. Oh, wait a minute. Weren't we supposed to maximize the area? Now this doesn't happen too often in a min and max problem, but we've actually found the minimum and it looks like there is no relative maximum. Well, what that means is we need to now check the endpoints. This is very crucial because we're looking for a maximum and this is a relative minimum. It's no good, which means that there is, of course, a domain. So something over here, maybe 0, and then some number we don't know. And one of these 2 points, either up here or up here, is clearly going to be where the maximum area is. So we should check into those points. We need to do a little investigation and see what we would get for those endpoints. Well, the one endpoint would mean that you had no square. So if you had no square and you cut the wire into all circle, then the radius would be equal to, well, x would just be 0. So we could, I guess, maybe we'll start with the original equation here. So we'd have the perimeter 10 would be equal to all circle. So 2 pi r. So r would equal 10 over 2 pi. which would be 5 over pi. And the area would be all circle, so it would be all pi r squared. So we'd get pi 5 over pi squared. So 25 pi over pi squared, which reduces to 25 over pi. So if there was no square and it was all circle, our area would be 25 over pi. Now if we did no circle, we would have, again, the 10 meters of wire equal to just x squared, or actually equal to 4x, the perimeter, 4x. So x would be 10 over 4, which is 5 over 2. So the area, that's the one, will be x squared, so 5 over 2 squared, which is 25 over 4. Now which one of these numbers is bigger, 25 over pi or 25 over 4? Well, 25 over pi, since pi is approximately 3.14, which is less than 4, 25 over pi is bigger than 25 over 4 because you're dividing by a smaller number. So this one right here, this is the maximum. So the maximum area doesn't happen on the interior, it happens at one of the endpoints. And the endpoint is where there's no square. So what is the optimum place to cut the wire? The final answer is don't cut the wire. Just make a circle. So a very strange answer here. The maximum for this problem is to actually do the endpoint, to not cut the wire at all and to just make yourself a big circle, no square at all. Which, if you think about it, if you're imagining a square or a circle, they're both pretty great shapes. The square is the best of all the rectangles. But of all the shapes, the circle is actually the best. If you're looking for getting the most area out of something, a circle gives you more area than even a square per amount of perimeter that you're using. The circle of all 2D shapes, this doesn't prove it exactly, but you can prove that the circle of all two-dimensional shapes is the best use of that perimeter. So if you're ever trying to make something, you're trying to maximize that area, this problem helps demonstrate that you should be using a circle. So hopefully you enjoyed this video. Make sure again you try those problems 1 to 22 for the minimums and maximums. And until next time, thanks for watching.